Morning, good afternoon, or good evening, whatever time you are going to be watching this video. I spoke to the class rep and I informed him that I'm unavailable even this week, as I'm not around, I'm not in town. So, but I still wanted us to just do a little bit of revision regardless. So in this video I'm going to talk about PCM, and I think, as I mentioned earlier, I said if there's one thing you're going to take out of digital communication 1, let it be pulse code modulation. Okay, this is a very important topic, and I know that a lot of you are still struggling to understand this topic, so I'm going to try and do a quick explanation and do some examples with you as well. So when we talk about PCM, or pulse code modulation, we're simply talking about the process of converting analog signals into a digital form. Okay, and that is done within the transmitter of the PCM block. I'm going to talk about the PCM block at the end of this video. So this conversion of a signal from an analog form into the digital form is done within the transmitter. Okay, and there are 3 major steps that are involved. So the first one is what we are calling sampling. And under sampling, you need to understand what sampling is and the sampling theorem. So you need to know how to state the sampling theorem as well as understand what it means. Okay, what does the sampling theorem mean? This equation over here is a mathematical expression of the sampling theorem, or the Nyquist rate. So so this statement here is saying Fs is standing for the sampling frequency. So the sampling frequency of a signal is equal to 2 multiplied by Fm, which is simply the maximum frequency that is present in a signal. Okay, the maximum or the highest frequency that is present in the signal. Now in the notes it's written as Fs is equal to 2W. Now take note, this is a capital W, not small letter, not a small letter W, capital letter W, which is standing for Fm. Okay, so in the notes this is what you will find, but this is also the correct mathematical expression. Okay, actually I prefer this one to this one because I know that some people might get confused with this W. Okay, so I have an example for you. This example is the one that is found in the notes. However, I've noticed that there's no solution that is in the notes. It's just a question. So this example, you can just refer to it. You go to page 16 of the notes and you will see the question. Okay, so you've been given this as an expression for a signal, and you're being asked to find the sampling frequency as well as the sampling period. Okay, so they can either say find the sampling period, or they would say the time interval between the samples. Still means the same thing. So sampling period and sampling frequency. Now before we are able to find the sampling frequency, we need to know what the Fm is, the maximum frequency that is present in the signal. Okay, so we are going to use this equation, but before we find Fs, we need to know what Fm is. How are we going to find this Fm, the maximum frequency that is present in the signal? We're going to look at what we have. Okay, the mathematical expression we have that is representing our signal. So we have x of t being equal to sine 3000t plus 2 cos 350t. We know that t stands for time. Okay, same thing here, t here stands for time. So we need to find Fs and Ts. So to find that, we first of all need to know the highest frequency that is present in the signal, okay, which is Fm. So I'm going to go back to this equation here. This equation, Fs is equal to Fm, and I need to know what Fm is. Okay, so generally this is how a general equation of a an analog signal will look like. Now take note, it's not that this is how these cosine and sine are arranged. So sometimes it might be sine, this W is a small letter w, not the capital letter W that we had later. So this is small letter w, and this is omega, it stands for omega. So you can have an equation which has signs throughout. So we have sine w1t plus another sine w2t. Or we can have an equation that has a cosines throughout. So we can have cos here and cos. So it doesn't really matter whether you have a sine or a cos, okay, in your equation. What we're looking for are the omegas that are present, okay, the angular frequencies W present in your signal. So if we go back to our example, we have 3000 T. So this 3000 is an omega, and we're going to call it omega 1 or angular frequency 1. And then 350 T, this 350 is also another omega. We're going to call it omega 2, being 350. Okay, so again I'm going to talk about these two here. These two in front of the cos should not change anything. Okay, what you're concentrating on are the numbers after this cos or after the sine. This number before the T, the number before the T is what we're considering as omega, which is angular frequency. Okay, so from the angular frequencies, this is where we're going to extract our frequency, because we know that the relationship between omega and the frequency is that omega is equal to 2 pi f. Okay, remember this equation, okay, or this relationship, very important. So from this relationship that we have, we know that we are able to find f. Okay, now what f are we looking for? Because we have two omegas, we have 3000 and we have 350. So what f are we looking for? We are looking for fm. I'm coming back to this equation. We are looking for fm, which is the maximum frequency or the highest frequency that is present in the signal. So if we go back to this equation, we have 3000, we have 350. We know that the higher number of the two is going to be 3000, sorry. Okay, 3000 is a higher number of the two numbers that we have here. So therefore I'm only going to concentrate on this omega 3000. Okay, omega 1 3000. So that's the one I'm going to get. So this omega, because this omega is going to give me a higher frequency of the two. So if I go back to this relationship that we have here, and I say omega, my omega is 3000, okay, is equal to 2 pi f. What I'm looking for is this f, because this f is what's going to give me fm, the maximum frequency present in the signal. So the only unknown I have here is now this f. Okay, I have 3000 is equal to 2 pi f, therefore I can divide both sides by 2 pi and 2 pi on this side, so that I am left with f. So meaning f in this case is a 477.5 hertz. So please do not forget your units, because we're looking at frequency, the unit is hertz. Okay, so W1, which is 3000 here, okay, W1 gives me the higher frequency of the two, therefore this frequency which I've just found here, 477.5 hertz, is my FM, the maximum frequency present in the signal. Now what I'm looking for is I've been asked to find the sampling frequency and sampling period. So if we're talking about sampling, these are the two most important parameters, Fs and Cs. Okay, so for me to find Fs, I'm going back to this equation which says Fs is equal to 2Fm, and I already have Fm here. So I simply replace my Fm and multiply it by 2. So this is the answer. In the test that we wrote, this is for full-time students. In the test that you wrote, I did not bring that equation. All I said was that the highest frequency of a signal was, I don't know the exact number, so I simply gave you the highest frequency that was present in a signal. So that meant that there was no need for you to do all this. I already gave you the FM. So all you needed to do was to replace that FM. I think should have been 5 kilohertz, if I remember correctly. It was 5 kilohertz. So all you needed to do was replace 5 kilohertz here and multiply it by 2. Now remember, if you say kilo, the kilo means kilo means 1000. Okay, so if you say 5 kilohertz, that simply means 5000 hertz. Okay, and this is where some people are making mistakes. They were simply just taking the 5. Okay, so if you please pay attention to these things. Okay, if it is a kilo, it means 5000. So in the test, all I did was give you already the highest frequency. So you needed to just replace in your equation. However, if this is the case, if you've been given an equation, you will need to figure out which one is your FM. Okay, so we have Fs being 955 hertz. So we already have Fs. The only one remaining now is the sampling period. Okay, so to find the sampling period, you use that formula. Ts is equal to 1 over Fs. Where is this one coming from? If I remove the S here, the S there and the S there, we know that we are simply talking about the period and frequency. So this is the relationship between period and frequency. We know that frequency is equal to 1 over period and period is equal to 1 over frequency. So it's the same thing. Okay, so for you to find Fs, if you have the correct Fs, then you also find the correct Ts. So Ts is simply 1 over 955, which you already found here, which gave me a 0.001 seconds, or you can write it that way, 1 by 10 to the power negative 3 seconds. So period is in seconds, frequency in hertz. So the equations that are important for you to remember, that equation, okay, Ts being equal to 1 over Fs, this equation, okay, Fs is equal to 2Fm, and this one, because you need to know the relationship between omega and frequency. Okay, so we have found Fs and Ts. I said these are the two most important parameters when we are looking at sampling. Why is that? Because when we're sampling a signal, a continuous signal that is of that form, this is your amplitude and the time here, t. Sampling is simply the division of this signal in equal parts. Okay, so these lines that I'm drawing here, these divisions, are what we're calling samples. And if we say the sampling frequency, we are simply saying how many times is this signal divided in these equal parts. How many times are we sampling the signal? That is sampling frequency. And then if we talk about the sampling period, sampling period, which is Ts, will simply be this space between the samples, that is your Ts. Okay, so no wonder I'm saying when we're talking about sampling, the most important parameters are Fs and Ts. Okay, so now let's come to the second part. Remember, I said there are 3 major steps that are involved in this conversion of a signal from an analog form to digital form. So the first part will be sampling, okay, and I've done some example to show you how we calculate Fs and Ts. The second major step under this analog to digital conversion is what we are calling quantization, okay. So quantization done by a device called quantizer. So while we were sampling, we were dividing. Now when you are giving a definition of sampling or quantization, please don't use the term dividing. I'm only using this to help you understand. Use the proper official definitions of these terms. Okay, so when we're sampling, I was dividing this signal in time domain. Okay, that is for sampling. When I start the quantization, we are now concentrating on the amplitude, okay, the y-axis of the signal. Okay, so when we're looking at quantization, quite similar to sampling, okay, in that we're still dividing this signal up, we're still cutting it into small pieces, but in this case we are looking at the amplitude of the signal. So as you can see, I've drawn these lines, these horizontal lines. I will need to know the size of this gap, okay, between these lines, and that size, or rather that gap is known as the step size, okay, the step size. And then I'll also need to know how many of these lines I need in this amplitude, how many times I'm dividing this amplitude, okay. Now the number of times I'm dividing that amplitude is what we're calling Q, okay. Quantization, Q being the number of quantization or quantized levels, okay. Q is the number of these horizontal lines, and then this delta is known as the step size, the space between the quantization levels. Okay, let me get my phone to focus. Okay, so I'm talking about quantization, and quantization is simply assigning integer values to the sampled instances. So we have these sampled instances. I said when sampling, we are dividing this signal, okay. So this is the sample, this one is the sample, and it ends up to here where it meets the signal, okay. This is another sample, it ends up to here. Now when you are quantizing, you are trying to find the amplitude of that sample, okay. Here we also want to find the amplitude of the next sample, so we need to know all the amplitudes of each sample. So we are assigning integer values to each sample. That's what we are doing under quantization. And under quantization, again, we have some formulas here. Remember, delta is the step size, which is simply this space between your quantization levels, okay. The space in between the quantization levels is what we're calling as a step size. So step size, or delta, is equal to the maximum, this is the maximum amplitude, minus the minimum amplitude over the number of quantization levels, okay. So Q is the number of quantization levels, and for you to find Q, you say Q is equal to 2 to the power n. Now that n stands for the number of bits that is used to represent each level. This n is dependent on the quantizer that is being used for this process. So if, for example, you've been told that you're using a 4-bit quantizer, that simply means that your quantizer uses 4 bits, 4 binary digits, the ones and zeros, 4 of them, to represent a decimal number. Okay, so if, for example, this first sample was a 5 here, if this is 5, instead of writing, so first of all we have 5, okay, but under quantization we're going to have 5, we're going to have integer values here. But when we go to the next step, which is encoding, this 5 will need to be represented in form of binary digits, okay. Now the number of digits that is being used to represent that 5 will be determined by the type of quantizer that you're using. So if you have been told that the quantizer that you are using is a 4-bit quantizer, that simply means that it uses 4 bits to represent a 5. Okay, so you have to, under encoding, this 5 will not just be 5 like that, you have to represent it in binary form. Okay, so let's look at this example. This question must have been in your test. That's for full-time students. I think this question was from your test. So it said something like a PCM system uses a 16 quantization levels. So it uses 16 quantization levels. What does that mean? That these lines here, the horizontal lines, are 16 of them. Okay, so if the horizontal lines, you've already been told that the horizontal lines are 16 of them, it simply means that you have already been given your Q. Okay, so you don't need to use this formula to solve Q. You already know that Q is equal to 16. Okay, and if Q is equal to 16, what is N? N is going to be 4. If Q is equal to 16, it means that your N is equal to 4. The number of bits that is being used by that quantizer is 4, because 2 to the power 4 is what gives you 16. Okay, now there's no need for you to start solving for Q. You've already been told your Q, so Q is already equal to 16. And then it uses, so your signal has an amplitude range of -4 volts to +4 volts. What does this statement mean? So this statement means that your highest, actually -4 is lower than negative. -4 is lower than +4. So -4 is the minimum and +4 is your maximum amplitude. So I'm sure you can see the shape of this signal. Now imagine, so this signal is just in the positive part. Now imagine that this went all the way down. Okay, so because if it had gone all the way down, that means that it was in between the positive part and also the negative part of this number line. Okay, so no wonder in that example we have -4, so -4 would have been somewhere here in the negatives, and then +4. So meaning -4 is your minimum and +4 will be your maximum. Okay, and you were asked to find the step size. So the step size is this delta. Okay, so we go back to that formula. So step size is equal to the maximum amplitude, in this case is +4, minus, so please take care, this is a minus, take care of the signs, this is a minus and not a plus. It's maximum minus minimum. Okay, so we have 4 minus, our minimum is -4, so please be careful. So it's 4 minus, this minus is coming from the equation there, and then the minimum is a -4. So therefore this will become a positive and to give you 8 over 16, which gives you a 0.5. So this is a unitless number, 0.5. What does that mean? this is a step size. Step size is equal to 0.5. So what that means is that, just wait for this to focus. Okay, so what that means is that this space, the space in between the quantization levels is 0.5. So if this is your 0, from 0, then this horizontal line that you're going to draw is going to be at 0.5. Okay, and then from 0.5, the next horizontal line you're going to have there, you're going to add a 0. So this is 0. Okay, the next one will be 0.5. Your next quantization level, you just add 0.5 to 0.5, it becomes 1. 1.5, 1, sorry, 1.0. So you're going to keep adding 0.5s, okay, until you reach the last quantization level. Which one will be the last quantization level? We've said we have 16 of them. Okay, so there's going to be 16 horizontal lines, and each space, the space between each of those lines will be a 0.5. So that's what is involved in quantization. Okay. Then the last step, which is called encoding. So under encoding, we are having these integer values that we found under quantization being represented by binary digits. Okay. Now for this semester particularly, I have not concentrated so much on encoding because I already know people are struggling already with sampling and quantization. Okay, for the previous semester we actually did an example of how you can encode, but we should just know that under encoding, the integer values are now going to be represented in a binary form. Okay, so let me go back to this example. We found that this delta was 0.5. That means that for every, between each quantization level, we have these 0.5s. Okay, so if the first one is 0, we have a 0.5, we have a 1, 1.5, 2, 2.5, until we have all the 16 levels. Okay, so that means that the highest, actually the highest amplitude should be, I think, 8 volts. Okay, so if this is my first sample, okay, and we've said that this is a 0.5, the next one will be a 1, and then the next one will be a 1.5. So let's ignore that 5, that was a different example. So this is 0, 0.5, 1.0, and 1.5. I hope people are not confused. I'm simply adding 0.5 to the previous number. Okay, so if this is what we have, and we have that one as our first sample, okay, so this sample is is coming up to here. So we have a 0.5 and then a 1 and a 1.5. So this sample is somewhere in between 1 volt and 1.5. So we can simply estimate this to be, let's say this is a 1.2 volts. So we're going to assign under quantization, we're going to assign integer values to all the samples that we have here. Okay, so we can do that by estimation, since this is not a very accurate drawing. Sorry. Okay, so once you have assigned all the samples with their integer values, the next will be to convert those integer values and represent them by the binary digits. Okay? So this is where I was saying that if you have something like a 5, okay, if you have something like a 5, you need to represent it in binary digits. So if, for example, you have a 1 volt, this is the simplest example I can give. Okay, if you have a 1 volt and you need to represent your 1 volt using 4 digits, 4 binary digits, it's going to be 0, 0, 0, 1. Okay, if you have a 2 volt, going to be, I think it should be 0010. Okay, so we are simply representing these numbers in form of bits. Okay, so that, remember, our aim is to convert an analog signal to a digital form, so that instead of sending the ones, two, we are now sending these ones. So if the first one, this sample, okay. So if this sample was 1.2, so instead of sending 1.2, the first sample will be represented by these digits. So this is what the transmitter is going to send via the transmission. So it will send this, and then it will send the next digits representing the next sample, which in this case will be probably this one. Okay, so that's what happens under encoding. So for encoding, we are now sending these bits over transmission line. Okay, so the 3 steps that I've talked about are all happening under the transmitter. Okay, if we talk about the PCM block, we are talking about